This is lesson number 12, Exploring Quadratic Functions, Introductory Explorations Part 1. We have now spent 7 lessons on linear functions. We know a lot about them. We know that algebraically, linear means y equals ax plus b, where the highest exponent present of x is 1. Geometrically, linear means a line. We are now ready to embark on a new exploration, that of quadratic functions and equations. Each time we go from one family of functions to the next, there is a progression, there is a link, and those connections you will form as we go along. Quadratic functions go back a long way in history. We know from the Rhine Papyrus, which is the oldest mathematical document we have today, that the ancient Egyptians worked with quadratic expressions. We know also from clay tablets that the ancient Babylonians were able to solve linear and quadratic equations. The ancient Greeks, coming back a little closer to nowadays, although it's still very far back in the past, we have Pythagoras, we have Euclid, we have Apollonius. And those are respectively 6th century, 4th century, and 3rd century BC. They represented quadratic expressions geometrically, just as we're going to do in this lesson. Then Diophantus, in the 3rd century AD, pushed even further the development of quadratic equations. A big landmark was Al-Khwarizmi, the Arab mathematician of the 9th century AD, who, borrowing from the East, the Hindu mathematicians like Brahmagupta, and from the West, the ancient Greeks, came up with the quadratic formula, which you will see in Algebra 2, but it really moved ahead the solutions of quadratic equations. And then, of course, we have, in the 13th century AD, in Italy, Leonardo da Pisa, who pushed it even further into the pre-symbolic stage. And finally, we have a list of Renaissance mathematicians whose names are Cardano and Viette in the 16th century, Descartes. We have Galileo in the 17th century showed that quadratic equations had many applications in physics. And the list goes on. Any list would be incomplete. So these are very, very old, 4,000 years old. Now, of course, the way they were written and the way they were called is not the way we're doing it today. That only started about 300 years ago, as we explained in the opening lectures. In this first set of introductory explorations, we are going to connect algebraic expressions with geometric shapes, in the spirit of the ancient Greeks. More specifically, we will represent with geometric sequences algebraic expressions that will turn out to be quadratic. 1, we will examine simple quadratic relationships. 2, we will make input-output tables for these relationships. And 3, we will look at the corresponding graphs of these relationships. For our first example of a quadratic relationship, we need to go to our mathematics laboratory, where it's all set up for us. Here you have a sequence of figures. Figure number 1, 2, 3, 4 corresponds to these figures. And we now have to fill out the area. The area will be the total number of square units represented by these square tiles that we use to make up the figure. I have purposely left space between the squares so you can see clearly what they are made up of. In the first example, we have 1 square unit, so the area is 1. In the second example, we have 2 rows of 2, so that is an area of 4. In the third example, we have 3 rows of 3 tiles, or 9. And in the fourth, we have 4 rows of 4, or 16. And those dots just mean that this sequence continues as far out as you'd like it to go. Now let's think of how we can write these numbers differently. 1 is just 1 times 1. 4 is 2 times 2. 9, we're borrowing from geometry here, is a square whose side is 3 and whose other side is also 3, so we can call that 3 times 3. And this one is 4 times 4. What I was saying earlier when I said 4 groups of 4, that's what we can write as 4 times 4. And finally, we can use a new notation. Well, it's not really new to you, but it's really pertinent to this lesson. This can be written 1 squared. This can be written 2 squared. This can be written 3 squared. And this 4 squared. And so on out to 5 squared, 6 squared, 7 squared, and so on. Well, now that you have seen these numbers, 1, 4, 9, 16, 25 would be the next, and 36, laid out as square arrays of tiles, I could have had beans, I could have had coins, I could have had dots, you now see clearly why these numbers are called square numbers. Or we say 4 squared, because way back 2,000-3,000 years ago, they were represented as a square. And what is the Latin word for square? Quadrus. That's the root of quadratic. So, when we'll have a quadratic expression, we will have a variable raised to the second power. It's as simple as that. We are now ready to generalize what we just discovered from our first exploration. For square numbers, if n is the figure number and a is the corresponding area, the algebraic or symbolic equation is a equals n squared. That's the squaring function. The input-output table for this quadratic function, consisting of the ordered pairs n, a, is as follows. 1 corresponds to 1, 2 to 4, 3 to 9, 4 to 16, 5 to 25, and so on. And don't forget to go back up and plug in the 0 and 0. We didn't represent that because that would just have been no tiles, but 0 squared is 0. Well, let's take this table that we just saw on the graphic and look at it a little more closely. Especially, let's look at how the x values and the y values change one with respect to the other. To do that, we need to go to our mathematics technology and look at that together. The change from this y value to this one, or output, is 1. The change here is 3. The change here is 5, and from 9 to 16 we have 7, and from 16 to 25 we have 9. We have changing values here. We do not have constant first differences, so this is not a linear function. I think we can pause for a moment now because I'd like to show you where these odd numbers show up. Notice the 1, 3, 5, 7, 9 are the increments and they are odd numbers. Let's go back to the table for a moment, our math laboratory, and show you these odd numbers. I specifically used different colors. You might have wondered why. 3 red is the increment from the green. 1 plus 3 gives me 4. When I go from 4 to 9, I add plus 5. Those are the yellow tiles. When I go from 9 to 16, I add 9. No, that's 7, sorry. This is 7. And then when I go from 16 to 25, I would add 9. So each time I wrap around a new odd number. Let's go back to our table and compute the second differences. From 1 to 3, we have a jump or an increment of 2. Same from 3 to 5, plus 2. From 5 to 7, another plus 2. And 7 to 9, another plus 2. So if you're starting to conclude that quadratics have second differences constant, you're getting there. Let us now go to the graphing calculator and represent these pairs of points in the geometric plane. Under L1, we have the values of n, the input values. We use n, as you know, for whole numbers. You could also call these x. Under L2, we have the squared numbers, or a, the area values. 0 squared, 1 squared, 2 squared, 3 squared, up to 6 squared. We can ignore column L3. That's for our next exploration. We're now pretty experts about this. So let's go to stat plot. Make sure that L1, L2 is turned on, which it is not. Now it is turned on. We then go to zoom. Zoom stat is number 9. And there are our points. If we were to trace them, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared, 5 squared, up to 6 squared. Those were the last input-output pairs that we keyed in. If we now go to the function and plug in the simple function x squared and we graph, we see that the function joins those points indeed. If we wanted to trace points outside of those few that we started with, we can turn the stat plot off. So that's number 4. It is done, and now we graph and have the function, which is our squaring function. We only have a piece of the function. We can't see the whole thing, but we will in a second. I like to trace that to show you that here, for example, where the spider came up, that's the square of 3. But then in between, we have all these other values. Any pair of x, y values that I would stop at, you now know that what you have over here, which is the y value, is the square of the corresponding x value. If we go to the window and change a little bit, go from -8, let's say, to 8, and from -3 to 36, we move back a little bit, make a larger window and graph, we get a nice idea of what the graph looks like. Now, this is the first time we're seeing such a graph. It definitely looks different from a line. It is curved. It looks like it has an axis of symmetry. It looks like the right side and the left side are symmetric, but let's think why. If I were to graph, for example, 3 squared, I would go 1, 2, 3, and that would be my 9. Well, over here at -3, you know that -3 squared is also 9. That's why we have a symmetry. All the positive values and the negative values have the same square values. This is called a parabola. We will have a chance to say that name over and over again. That's the graph of a quadratic function. Lastly, what I'd like to do is zoom in around here. So let's go to zoom, select 2 for zoom in, and let's do that. I'd like to just show you that the function stays right above the x-axis except at 0. So it comes down to the x-axis and then goes back up but never goes below. We are now ready to embark on our second exploration for the day. These were square numbers. We're now going to something new, oblong numbers. For that, we need to go back to our math laboratory. And as before, we have the n value, which is the figure number, and A is the area of each figure. Figure 1 has 2 square units, so we can put 2. Figure 2 has 2 rows of 3 or 6. Figure 3 has 3 rows of 4 or 12. Figure 4 has 4 rows of 5 or 20. If you see 1, 2, 3, 4, 5 times 4 is 20. Now, last time it was very simple to come up with an expression breaking these numbers down because we had squares. Here we have rectangles. Well, we can also borrow from geometry as the Greeks did. We know that when we want to compute the area of a rectangle, of course you imagine that these tiles are closer together and stuck to each other, but we've left them this way for better visualization. Over here we have a rectangle of 1 by 2, so we can write that as 1 times 2. Here we have a rectangle of 2 by 3. So that's 2 times 3. Over here we have 3 times 4. And finally here we have 4 times 5. What I'd like you to notice is that the first number in each of these products corresponds to the n number. So 1 is 1 times 2, 2 is 2 times 3, 3 is 3 times 4, 4 is 4 times 5. Well, since this goes on and on and on, what would we write for the nth figure? Well, the nth figure would give us n times the next number, but the next number is n plus 1. Now we have a little algebra to do here. We've seen that this is called the distributive law. N times n is n squared, and n times 1 is n. And here is our second quadratic expression for today. We can now state the result from this second exploration. For oblong numbers, if n equals the figure number and a the corresponding area, a equals n times n plus 1 equals n squared plus n, where n squared is the quadratic term and n the linear term. The corresponding table of input-output values for this relationship, for this quadratic relationship, is as you see. On the left column, I have the input, or the n. On the right column, the output, or the a. For 1, I have a value of 2. For 2, an area of 6. For 3, 12. For 4, 20. And for 5, I would have had 30. 5 times 6 is 30. And going back up to the 0, what would 0 be? Well, 0 times 1 is 0. Let us examine now more carefully, more closely, the rate of change of these two columns. How is y changing as x changes? Back to our mathematics technology. The change in y, or output, from 0 to 2 is plus 2. The change from 2 to 6 is plus 4. The change from 6 to 12 is 6. Then we have 8, and then we have 10. Notice that as before, just like before, our changes here are constantly 1. So again, we have first differences that are not constant, so this is not a linear function, yet they change in a very nice pattern. We actually notice that this time we have the even numbers, 2, 4, 6, 8, 10. Last time we had the odd numbers. Let's go very quickly back to the table, the math laboratory, and look and see where we can find these even numbers. If we go back here, from 0, which was nothing, to the first, we had a change of 2. From the first to the second, we augmented, we increased by 4. There are your 4 tiles. From figure 2 to 3, we increased by 6. And there are your 6 tiles. From 3 to 4, we increased by 8. And there are your 8 blue tiles. If we kept on going, we would wrap around each time with the next consecutive even number. Back to our input-output table to compute our second differences. From 2 to 4, we have an increment of plus 2. From 4 to 6, another plus 2. From 6 to 8, another 2. And 8 to 10, another 2. Once again, our second differences are constant, equal to 2. Now, just because the 2 first explorations gave us a second difference of 2 doesn't mean it will always be 2. It just happens to be in these 2 cases. The other thing I wanted to mention about an oblong number, it's a rectangular shaped number where the width and the length differ by 1. Let us take these pairs of values, go back to our graphing calculator, and plot them and see what type of a function we have. Do we have the shape of the previous one, or do we have something else? Here we have the values of input, or x values, and the values of the output, or y values. L3 and L4 is exploration number 2. This is again for the next one, so ignore L5 for now. If we go to stat plot to plot these, we want L3 and L4 to be plotted, so let's turn 2 on. We go to zoom stat, always the same procedure, number 9, and there are our points. If we were to trace them, we find the first figure, the second figure, the third, the fourth. The fifth figure was not on the board. It would be 30, because 5 times 6 is 30, and the sixth figure would be 6 times 7, or 42. If I go to the y equals function and key in the function x squared plus x, which is what we found, we can now graph the two, and they go right through those points. If I want to consider all the values in between, not just the whole numbers, always this transition from the discrete values to the continuous values, I can turn stat plot off. That's number 4. It is done, and now we can graph it. Now this no longer represents just those figures that we saw, but it represents any x value, and the y would represent x squared plus x. If we wanted to step back a little bit and change the window to see all of it, we would have, let's say we have a bigger window of -8 to 8, and suppose we took, for a minimum y value, -3 to 42, as we saw was our largest value. Let's make sure our stat plots are off. They are, and now we can graph the function. Again, we have a parabola. The difference is that it looks like this might not be the axis of symmetry. It's a little shifted to the left, but some vertical line, nevertheless, would be the mirror or the axis of symmetry with respect to the two branches. Let's zoom in finally to see what happens down here. So let's go to zoom. Zoom in is number 2. In this case, the function goes below the x-axis. Now these are details we're going to see later, but it's interesting to keep in mind that sometimes the function is above, sometimes it will have more than one intersection. It clearly looks like the function is below here. If we wanted to trace a little further, we could trace and zoom in again. One more time, zoom in. And then we definitely see that the function goes below the x-axis. All right, we are now ready for our third and final exploration. We need to go back to our math lab to look at this third geometric sequence. It is the most elaborate of all three, so put your gray matter to work and work with me. Here we have 4 figures. The area of the first is 1. The area of the second is 1, and 4 red makes 5. The area of the third, we have 5 plus 8 more yellows. That gives us 13. Then we have 13 up to the yellow. We add 4 and 4, 8, 9, 10, 11, 12. We add 12 blues, and that gives us 25. Now, unlike before when we had squares or rectangles, and it was very easy to find an expression, a general expression, so we can generalize beyond number 4, here we have more elaborate or complicated figures. So let's do a little manipulation. Watch this with me. I'm going to make 2 squares. So let's move this one a little to the left. Here, if we move these up here, and this one up here, we have 2 squares again. And over here, we move these up here, and these over here. Let's see what we have. Here we have, at 1, we have 1 squared. At 2, we have a 2 square and a 1 square. At 3, we have 3 squared. There we have a 3 by 3. And we have a 2 by 2 that comes from that same picture. Over here, if we divide these up, we have a 4 squared and a 3 squared. So we can use the information that we had from before. We know how to express squares. So at 1, we have 1 square and nothing next to it, so we can call that 1 squared plus 0 squared. Over here, we have 2 squared and 1 squared. So that's 2 squared plus 1 squared. Over here at the third figure, we have a 3 by 3 squared and a 2 by 2 squared. So that's 3 squared plus 2 squared. For the fourth one, we have a 4 squared and a 3 squared. So that's 4 squared plus 3 squared. Now we can generalize and say that when we're at the nth level, we will have n squared plus the square of the number before n. But the number right before n, the integer before n, would be n minus 1 squared. So we need to work this out. We need to expand this so we can write it as a polynomial. So let's go to our transparency and work that out. We have n squared plus n minus 1 squared. That equals n squared plus, this is the square of a difference, which we've seen before. It's n squared minus 2 times the product, that's 2 times n times 1, which we don't have to write, plus 1 squared, which is 1. We now combine the n squares. That gives me 2n squared minus 2n plus 1. Here is the quadratic formula, or rather I should say the quadratic expression, which is our third quadratic function of today. Let me point out that this is again the quadratic term. This, as always, is the linear term, and this is the constant term. We can now generalize what we've just found. If n equals the figure number for this third exploration, and a the area, the a function equals 2n squared minus 2n plus 1. The corresponding input-output values for this quadratic function is 1 gives 1, 2 gives 5, 3, 13, 4, 25, and if I had done the fifth geometric figure, I would have had 41. That would be 5 squared plus 4 squared. And again, don't forget the top one, 0, 1, because when I take 0 squared plus negative 1 squared, I get 1 squared. I would like you to take the time to examine the table more carefully, look at the change in x, look at the change in y, and see if the first differences or is it the second differences that are constant. Also take the time to graph the function, see if we get a parabola again. So we have seen 3 quadratic functions. We are ready to recapitulate. The first was y equals n squared, the second n squared plus n, and the third was 2n squared minus 2n plus 1. If we go from n to x, from the discrete variable to the continuous variable, we can write those same 3 functions as f of x equals y, which equals x squared. The second one is f of x equals y equals x squared plus x. And the third is f of x equals y, which equals 2x squared minus 2x plus 1. We are now able to generalize and give the standard form for a quadratic function. That is f of x equals, or y equals, ax squared plus bx plus c, where a, b, and c are the constants, and x and y are the variables. In the next visual, you see the evolution from the linear to the quadratic. In the linear case, we had ax plus b. Ax was the linear term, b was the constant term. In the quadratic, we have 3. Ax squared, the quadratic term, bx, the linear term, and c, the constant term. The linear and the quadratic functions are the first 2 families of the class of polynomial functions. I hope you've enjoyed our geometric explorations of quadratic functions, where we connected geometry to algebra in the spirit of the ancient Greeks. Take some time and explore further geometric figures. See if you come up with linear functions, with quadratic functions, or with something completely different.